This is Learning Assessment Problem 7.5. In this problem we have a capacitor of value 2 micro. In this problem we have a 2 farad capacitor, a switch which opens at time equals 0, and we're asked to determine the time behavior of this voltage V sub O across a 2 ohm resistor. The problem solving strategy will be that of first order transient circuit solution using the step-by-step approach. So the step 1 is to assume that the desired voltage VO of t is of the form K1 plus K2 e to the minus t over tau, where K1, K2, and tau will be determined in our next steps in this process. The first step in the process is to assume the form of the voltage VO of t is equal to K1 plus K2 e to the minus t over tau, where the K1, K2, and tau are coefficients to be determined in the following steps. In step 2, we look at the circuit conditions at t equals 0 minus, and we'll want to find the condition of the capacitor VC at 0 minus. So we'll use nodal analysis. Consider a node voltage V1 at the top of the switch. The switch is still closed, recall that, and steady state conditions prevail here. So the capacitor looks like an open circuit under these conditions, and we could ignore its presence in the circuit analysis for the moment. So we'll write an KCL equation at the node V1. We're using the bottom of the circuit as our reference. So we have V1 times 1 over 2. So we have V1 divided by 2 ohms plus V1 minus 8 volts divided by 2 ohms plus V1 minus 12 volts divided by 3 ohms is equal to 0. Here we're ignoring the presence of that additional node between the 2 resistors for the moment. So we have V1 1 over 2 ohms plus 1 over 2 ohms plus 1 over 3 ohms is equal to 4 amps plus 4 amps, or 8 over 6 ohms. V1 is equal to 8 amps, and this gives us that V1 is equal to 6 volts. Now we can determine the voltage VC across the capacitor, and we'll obtain that by taking the 12 volt source and subtracting the voltage drop across the 1 ohm resistor. Consider a current I2 flowing from the 12 volt source to the node V1. We'll have that I2 is equal to the 12 volts minus V1 divided by 1 plus 2. This is equal to 12 volts minus 6 volts divided by 3 ohms, and I2 is equal to 2 amperes. Now we can say that VC at 0 minus is equal to 12 volts minus 1 ohm times I2, the current we just determined, or VC 0 minus is equal to 12 volts minus 1 ohm times 2 amperes, VC at 0 minus. VC at 0 minus is equal to 10 volts. Now we proceed to step 3, in which we look at the circuit condition at time 0 plus. We're using the concept that VC at 0 minus is continuous across the switching interval. This is the same as VC at 0 plus. And in this step, we wish to find the variable of interest at time 0 plus, that is VO at 0 plus. So in this instant, we'll replace the capacitor with a voltage source equal to its initial value at 0 plus. So this will be 10 volts. And we wish to determine the output voltage V sub O at this time. So we can say that by voltage division, we have 10 volts appearing across the two 2-ohm resistors. So we'll have VO at 0 plus is equal to 2 ohms times 10 volts divided by 2 ohms plus 2 ohms, or VO at 0 plus is equal to 5 volts. Step 4 will consider what happens as time goes to infinity for the output voltage VO at infinity. In this case, the capacitor again is in a steady state condition, so it looks like an open circuit. The switch has been opened, so it no longer is in the circuit. And again, by voltage division, we can obtain this output voltage VO at infinity is equal to VO at infinity is equal to 2 ohms times 12 volts divided by 1 ohm plus 2 ohms plus 2 ohms, or VO at time infinity is equal to 24/5 volt. Or VO at time infinity is equal to 24/5 volt. In step 5, we wish to determine the time constant for this circuit, and that is, for the case of the capacitor circuit, tau is equal to R Thevenin times the capacitance. These are the terminals for the capacitor, and we want to find the Thevenin resistance looking into those terminals. We set the voltage source to 0, and we'll find that R Thevenin is equal to 1 ohm in parallel with 2 ohms plus 2 ohms, or R Thevenin is equal to 1 times 4 divided by 1 plus 4 is equal to 4/5 ohm. Then the time constant tau is equal to R Thevenin times the capacitance. This is equal to 4/5 ohm times 2 farads, And this gives us the time constant for this circuit is 8/5 second. In step 6, we put all of this together. Recall that we assumed that VO of t was equal to K1 plus K2 e to the minus t over tau. So we have VO at 0 plus in this expression is equal to K1 plus K2, and we found that that is equal to 5 volts. Likewise, VO at infinity in this expression is just the K1 coefficient, and we found that that was equal to 24/5 volt. So we can use those two equations to determine the coefficient. K2 is equal to 5 volts minus 24/5 volt, or K2 is equal to 1/5 volt. Writing our assumed solution form, we have VO of t is equal to 24/5 plus 1/5 e to the minus t over 8/5, or VO of t is equal to 24 over 5 plus 1/5 e to the minus 5t divided by 8 volts, and this is good for the time interval t greater than 0.